Hello and welcome back to this discussion for nuclear reactor heat transfer. We're going to talk a little bit today just about dimensional analysis of our boundary layer equations. Now, the analytical solution to these equations is actually pretty complex. However, we can just look at dimensional analysis here to obtain some insight into the behaviors of these equations. So we're going to define dimensionless variables, look at something like the dimensionless variable x star, which is x over some length scale, and the dimensionless variable u star, which is the velocity over some v length scale, capital V. And we can define all these dimensionless values, and when we do that, we can substitute them into the equations and then rearrange them. And that gives us a set of equations that looks something like this. And this shows us from fluid mechanics, we have the Reynolds number. However, from heat transfer, we also obtain a new dimensionless number, the Prandtl number. We talked about the Prandtl number in the previous video, and it's the relationship between the kinematic viscosity and the thermal diffusivity. So this actually confirms our analysis from our discussion on introduction to the boundary layer, thermal boundary layer, and shows that we can use that to analyze boundary layer behavior. So now we're going to look at comparing the friction coefficient with the heat transfer coefficient. Now, for the friction coefficient, we take this equation for wall shear, and we convert this into a dimensionless form as well. We define the dimensionless velocity, dimensionless y coordinate, and that gives us something that looks like this. Then we can rearrange these terms to define the wall shear as the friction coefficient. So we come up with the definition of friction coefficient with respect to wall shear. And we end up with this expression that the skin friction coefficient is 2 over Reynolds number, and then this dimensionless velocity gradient turns into this function of Reynolds number. We could do a similar analysis for the Nusselt number. If we actually look at the definition of the heat transfer coefficient, we have our typical convection boundary condition, and this is the conduction into the fluid from the wall. So if we take a look at this equation, again, we're going to convert it into a dimensionless form, and when we do that, we end up with an equation that helps us define the convection coefficient that's analogous to the wall shear equation. Only this time it's our dimensionless temperature gradient instead of our dimensionless velocity gradient. So once we've done this, we can define the Nusselt number by just arranging this to get our dimensionless ratios. So now we have the Nusselt number, which is some function of the temperature gradient, which is a function of Reynolds number and Prandtl number. So here we have skin friction coefficient is related to Reynolds number. Here we can say that the Nusselt number depends on the Reynolds number and the Prandtl number, which again confirms our analysis from the previous slide. So the Nusselt number is important. It represents the ratio between the convection and the conduction into the fluid. And it measures the enhancement of heat transfer due to flow, the enhancement of heat transfer compared to a non-flowing substance. I also want to note here that the subscript on the Nusselt number typically represents the length scale required for the Nusselt number. So a Nusselt number sub x is going to use x as the length scale here. If it was a Nusselt number sub d, then Nusselt number sub d is going to use the diameter of whatever the object is. Typically we use Nusselt number d for spheres and cylinders and so on. We can also look at dimensional analysis to provide what we call the Reynolds analogy. As engineers, we're primarily interested in finding the skin friction coefficient, which gives us the drag force, and h, which gives us the heat transfer. So for the Reynolds analogy, we assume that the Prandtl number is equal to 1 and that there's no pressure gradient. Then we have exact analogy between the momentum and energy equations for our thermal boundary layer. And under these assumptions, then the energy and momentum equations are exactly identical, and the solution will be identical. And this allows us to use solutions from fluid mechanics to predict the heat transfer coefficient. So we can use either one of these equations. They're roughly equivalent. One is based on the Nusselt number, and one is based on the Stanton number. The Stanton number is just an alternate method, or alternate dimensionless parameter for correlating heat transfer coefficient. So you can say that CF, the skin friction coefficient, is equal to Nusselt number, or in this case, the skin friction coefficient is twice the Stanton number. Either one of these two is valid.